Okay. So one of the things we know in our houses, like if you have a 2-story house, if you go up in your house, it's going to be warmer. Ours is. It's kind of an older house, and if we go in our basement, it's colder. Now, I kind of think that works with this. Warm air generally will rise. The reason warm air rises actually is because if we think of, and we're talking more about this, if we have 2 chunks of air, okay, and if this one is cold and this one is H for hot, actually the cold one, the little chunks of the little air particles would be close together. They're like, somebody told me one time they're like shivering, they like nestle to each other. A chunk of air that is warm, actually it's what we say less dense. It's less dense. And kind of like if you have 2 things in liquid, or if you have 2 liquids and you let them mix and then you let them kind of separate, the one that's less dense will rise. And that's exactly what warm air does, it rises. So here are these hot air balloons. They're not helium, they're hot air. So basically inside of here we have air inside each one of these, just regular old air. And then down here, some of you guys may know this, down here at the bottom they actually have a little fire that just heats the air. And so basically what's happened in each one of these balloons is that air is less dense. So if I could see those particles, okay, they're farther apart than the particles here. This is colder, this is hotter. That's why hot air balloons rise. Hot air balloons are what we call basically an unstable situation. The video we watched talked about the different types of clouds. Some clouds form in a stable environment. Some clouds form in an unstable environment. Actually, or an stable air. We're going to see that, remember the video, and we'll talk more about this hopefully tonight. The types of clouds that form in stable air basically are your flat ones. They're like your stratus clouds. And unstable air will give you your fluffy ones. That's your cumulus clouds. Ooh, cumulus. These are fluffy. And these are flat. But it's kind of like stable air won't want to rise. Unstable air will want to rise. And so you get these 2 different types of clouds. So stable air will not want to rise. The reason stable air won't want to rise basically is that chunk of air, and you can try to get it to rise and it will start to rise, but it will have a tendency to want to stop because unlike the hot air balloon, it's cooler than its surroundings. Okay? Unstable air is warmer than its surroundings. So that's why I said hot air balloons are kind of like an unstable sort of mini little atmosphere. They're unstable because they're warm compared to right outside the balloon. So we're going to talk about 3 types of instability, and you're going to hear me kind of go back and forth. So here where, for instance, this term right here, absolute stability, you're going to hear me call it absolutely stable. I hope you can kind of work with me there. Absolute stability is the same thing as absolutely stable. I don't know. Absolutely unstable is the same thing as absolute instability. So you'll see what I mean. But I'm going to go ahead and tell you ahead of time that each one of these, the types of stability, it has to do with what the ELR is. Question mark ELR. That's totally it. You're like, I thought you said, Mrs. Snipes, the ELR was 5 degrees Celsius per kilometer in the troposphere. I did, but I said you have to send up a weather balloon to know for sure. And what that ELR is actually drives what sort of stability the atmosphere is. So that's why weather balloons are so important. Weather balloons, I think I might have mentioned it, go up twice a day at locations all around the world. They go up about the same time. If you're like, dude, it's time to send the weather balloon up, you're like, oh, not again. Okay? So that 5 degrees Celsius cooling in the troposphere for every kilometer you rise, I need to revisit that because that is so not the real deal, okay? All right. So we're going to be running into this concept again of a temperature inversion in Chapter 4 and in Chapter 5. We said, or you guys learned that with regard to the atmosphere, hopefully on your test you put troposphere, stratosphere, thermosphere, and, troposphere, stratosphere, mesosphere, and thermosphere. And they basically have a zigzagging sort of thing where if you go up in the troposphere, basically it gets cooler. So it goes like this. As you go up in the stratosphere, it gets warmer, cooler, warmer, that sort of thing. If we have temperature down here, cooler, warmer, as you're going up. Cooler, warmer. Now, you heard him say on the video that basically all clouds are kind of confined to the troposphere, basically. And that actually has something to do with as they reach, and we heard it on the video, as you start to actually are over, this is my thunderstorm cloud, has kind of a flat top up here, that's an anvil, has kind of a flat bottom. This is my storm cloud. This right here, reaching into the stratosphere, clouds don't like to poke above the tropopause because they actually, this right here starts a temperature inversion. What is a temperature inversion? As you go up, it gets warmer. That's a temperature inversion. The stratosphere is one big temperature inversion. Can we have temperature inversions in the troposphere? Yeah. And we're going to see basically then, if this is my troposphere, as you go up, it gets warmer and then it gets cooler. There's like a kink. Okay. This right here is a temperature inversion. Okay. It gets warmer instead of getting cooler. So keep that in mind. That will come up again. All right. So this is an example. You see the caption is this profile actually fits a scenario where the environment is stable. So let's see what that looks like. So this figure actually has the environmental lapse rate at 5 degrees Celsius per kilometer. Okay. So then to kind of reveal what the environment's doing, we have 25 degrees Celsius, and then it cools to 20, and then it cools to 15. I buy that. So we're going to use one of our lifting mechanisms, 4 lifting mechanisms, to get this chunk of air to rise. Okay, and I can see kind of by the outline there's no precipitation. So this is all going to be at the dry adiabatic rate. So it's going to go from 25 to 15, okay, and then 15, of course, to 5. Oh, sorry, 15, yeah, to 5. Okay. So this right here, we're seeing an application of the dry adiabatic rate, just 10 cooler, 10 cooler. And then what you need to do to understand its stability or instability is basically compare this temperature over here, do kind of like the hot air balloon check, okay? Now they're equal, okay? Here, okay, it is actually colder. If this is colder, then this does not want to rise. Here, it's still colder. It does not want to rise. Okay? So we can make it rise by one of our lifting mechanisms, but it's not, it fails the hot air balloon test. Okay? So that's why in this particular scenario, what we say the tendency is for it to want to actually go down. Okay, it's fighting that whole rising and cooling. Okay, so that's why we say that the environment is stable. And actually, there are 3 conditions, and this is the first of the 3 conditions. So absolute stability. That's kind of why I clear this off. Because I want to kind of sum them all up. We say the atmosphere is absolutely stable, or, okay, ELR is less than, so I'll put a less than sign, your wet adiabatic rate. Okay? It's all about the ELR. And this slide just kind of goes on to kind of talk you through that. Okay, if that's the case, then you can use a lifting mechanism if you want. But basically, it's going to cool at a rate that will keep its tendency want to sink. Okay, so it will be stable. And if you have a temperature inversion in place, then that actually is going to be the situation. Okay, absolutely stable. So if it's absolutely stable, kind of thinking ahead when we talk about severe weather, you're not going to get your in order to get your thunderstorm cells, your thunderstorm clouds, your tornadoes, your hail, your lightning, you need to have unstable air. That's not going to do it. Okay, this one is now looking at absolute stability. Or this actually is absolute stability, sorry. Okay, so let's see. It's exactly the case we looked at before, just kind of expanded. Okay, so can you guys kind of see these clouds right here? So actually we are gonna have precipitation, so we are gonna have to do both, first the dry and then the wet adiabatic cooling rate. So we're gonna start, along the side there. It's just to kind of show you that when the balloon went up, it picked up 20, 15, 10, 5, 0, -5. Basically, it cooled like clockwork, 5 degrees Celsius for every kilometer. I wonder if it really does that, but okay. Okay, so this is where, and actually on that board over there, I kind of warned you, don't blame me, but your author, and rightfully so, I guess not in the same textbook, he shouldn't, but switches from a wet adiabatic rate when it starts to condense. Instead of 5, he goes with 6. So we'll just have to kind of go with him. So here we go. So we start at 20, no condensation, okay, for the first couple of elevations. Okay, so it cools at the dry adiabatic rate. It's at 20, okay, it cools to 10, and then it cools to 0. Now I can start to see clouds, but remember now we're going to cool at 6, not 5. So it's going to go from 0 to -6. Okay, actually the first time I did this I was like, are you serious? Okay, so notice that we have a cooling rate starting right here of 6 here, and you're like, well, how would I know that? Well, look at the figure. Okay, it's reached it's cooled down to the dew point temperature, and you see clouds there. Okay, so this is cooling at the wet adiabatic rate, and this is cooling at the dry adiabatic rate. Now, to do the whole hot air balloon check, what we need to do is to check each one of these elevations with its environment. So, for instance, if we check, well, 20 against 20, that's equal, right? Okay, 10 against 15, that is cooler. 0 against 10, that is still cooler. -6 against 5, okay, I'm getting cooler here. So if you were, it kind of, like I said, fails the hot air balloon check. The environment is warmer, okay, it's like the inverse of a hot air balloon, than the chunk of air. So that's why you can get it to rise. You can have some sort of frontal lifting or orographic lifting or convergence, you know, and you can get it to go ahead and condense, but it's not going to want to necessarily rise on its own. Its tendency is to go back down. Okay, so over here, for each of these now, what your author's done is the purple line is what the weather balloon said. Okay, the purple line is basically what is the temperature of the atmosphere. Okay, and these are the various elevations. Okay, so you can kind of see the nice slope, nice straight slope, 5 degrees. That was the ELR, 5 degrees for every kilometer it rises. This right here, the reason you see two different colors is right here it cools at 10, and right here it cools at 6. It's kind of a jag. Okay. So I think maybe the reason your author went with 6 is we said if your environmental lapse rate is less than your wet adiabatic rate, okay, and here he's going with an wet adiabatic rate of 6. So that kind of worked for him. Boy, I'm getting markers all over the place. I'm going to say 5 degrees Celsius per kilometer or 6 degrees Celsius per kilometer. Okay. Sometimes students will say on a test, Mrs. Snipes, what do you want me to do? And I think I usually tell them 5, or I probably won't put you in that situation, so I have to figure it out. Okay. So this is my little slide to kind of show you, you know, a little bit what we're up against. This was the slide we last looked at, and it's cooling at 6 degrees Celsius for every kilometer it rises. This is the slide we looked at earlier. It's cooling at 5 degrees Celsius for every kilometer it rises. That's okay. If that's the worst thing that the textbook has, we're in good shape. Okay. Now we are going to look at absolutely unstable. See, I like that term, absolutely unstable, instead of absolute instability. And again, it's going to be about the ELR, and here we go. If the ELR is more than the dry adiabatic rate, so here we go. ELR, that's the weather balloon thing, has to be more than the dry adiabatic rate. And the dry adiabatic rate is 10 degrees Celsius per kilometer. If that's the case, then you're going to see that it's absolutely unstable. Okay? And I'm going to kind of show you with a picture why this is. But at every elevation, because of the environmental lapse rate, at every elevation, whether your cloud is condensing or not, you're going to do your hot air balloon check, and you're going to see that it's warmer than its environment. Okay? I'll prove to you. Well, I have an example coming up anyway.
Oh, that's the last one.
Oops, sorry.
Okay, I got it.
Cool. So, here's the picture. And it looks like we're doing convective lifting here, maybe. Got the little sun shining on the little patch of air there. This diagram shows you absolute instability or absolutely unstable. Okay. The environmental lapse rate is greater than the dry adiabatic rate. So what your author's chosen is 12. That's cool. The weather balloon, no pun intended. The weather balloon said that as you go up, for every kilometer you rise, it's going to cool 12. So it's going to go from 40 degrees Celsius minus 12, that's what, 28? Okay. Minus 12 is 16. Minus 12 is 4. Minus 12 is negative 8. Okay? So the environmental lapse rate of 12 is definitely greater than 10. So let's see what this looks like. And you can already see kind of the lifted condensation level. Right? So it starts at a toasty 40 degrees Celsius. Notice it's not condensing until it actually reaches 2 kilometers. So for the first 2 sets, it's going to cool at 10 degrees Celsius. So it's going to go from 40 to 30 and 30 to 20. There, about 2 kilometers, we see cloud. So now when it goes from 2 kilometers to 3 kilometers, it's going to cool now at, I think he goes with 6. So it's going to go from 20 minus 6 is 14. Okay, 14 minus 6 is 8. Okay, so that's kind of where that comes from. So let's check to see, let's do the check here now. At each elevation. So This really doesn't count. They're both at 40, so we'll put equal. Now at 1 kilometer, we have 30 and 28. Ooh, by 2 degrees, our chunk of air wins. Here we have 20 and 16. Ooh, 4 degrees, chunk of air wins. Here we have 14 and 4, 10 degrees. Okay, here we have 8 and -8, 16 degrees. Okay, so it passes the hot air balloon test. Okay, that chunk of air is unstable in the sense that it wants to rise. It's warmer than its environment. And it will most likely or possibly rise clear to the tropopause, okay? And depending upon the punch it has, it could even punch through the tropopause into the stratosphere. And have you ever, I know you guys have seen the thunderstorms that have kind of this cauliflower looking thing, kind of like, and actually that's what we call an overshooting top. And it kind of speaks to the instability. Okay, so that's absolutely unstable. Cool. So if we were to kind of look at the purple again, is the environmental lapse rate, what the weather balloons spit back. Now notice everything, the red line is where it is cooling at the dry adiabatic rate, and the blue line is where it's cooling at the wet adiabatic rate. But notice they are all the time, if this is the temperature of the parcel of our air that's rising, it's all the time to the right of or warmer than the environment. So that's kind of what that's emphasizing. All right, conditionally stable. You know, I got a different word for everything. I'm like my mom, she's got different words for everything. So, conditionally stable. Otherwise known as conditional instability. Now you might be wondering, now Mrs. Snipes, if there's really 2 words for them, what am I going to do? Which one are you going to do on the test? And I don't know, I'll have to figure that out when I make out the test. Okay? But conditionally unstable, I like that better because basically, how do I say this? If I understand it right, it depends upon the moisture of the air. That's the condition. Will it be stable or not? It kind of depends. Okay.
Is it stable or unstable?
It depends on the moisture of the air. Conditionally, oh, thank you. Conditionally unstable. Thank you. That's what I meant to say. Good catch. And this depends on moisture. But in general, let's see. In general, we can actually say it is between. So the ELR is between 2 things. And you're like, what? How do I do that? So it's greater than something, but less than something else. And you're like, how would I know which to do? Well, which one was smaller? The wet adiabatic rate? Dry adiabatic rate was larger. So actually you can kind of write it as a 3-way inequality like that. So it's got to be between 5 degrees Celsius or 6 degrees Celsius per kilometer and 10 degrees Celsius per kilometer. Okay, so it's kind of limited. There are not a whole lot of choices there. So let's see what your author does. So he picks 9, which that's a safe number, I suppose. So let's look at kind of its stability or instability here. Okay, so 9 then, we kind of have this going up from 1,000 meters to 5,000 meters, from 1 kilometer to 5 kilometers. This is cooling at 9 degrees Celsius per elevation. Here we have until, looks like 2 kilometers, it's going to cool at 10 degrees Celsius, okay, the dry adiabatic rate. Then beginning at 2 kilometers, we're going to kick into cooling at 6. Okay? So it goes from 20 to 14, 14 to 8, 8 to 2. So let's do a check here, see what we got with regard to, let's do the hot air balloon check. Okay, these are equal, like they have been. Now, 30 and 31, I got this one. I got our air is a little bit cooler by 1 degree. Here, at 20 and 22, our air again is cooler. Its tendency actually over here, the tendency at the first 2 elevations is down. Now, when it starts to condense, and this is why I said it kind of depends on moisture, because when it starts to condense, then we actually kick in with the latent heat is released, and so actually cools at a slightly less rate, 6 instead of 10. So here, if we compare 13 to 14, aha, right there, finally, by 1 degree, it starts to be like a hot air balloon. It goes up another kilometer, and again it's hotter by 4 degrees. It goes up another kilometer, and it's warmer by 7 degrees. Okay, so this actually right here, this is a flipping point. Okay, so it's conditionally stable. And I'd have to double check and convince myself. But to me, if it would rise, let's go ahead and do it, let's convince ourselves. What if it didn't, what if condensation didn't begin right there? It would go up to 3 kilometers, and instead of 14, it would be, what, 10? Right? In that case, it would be cooler. Does that seem right to you guys too? And then if there was no condensation at 4 kilometers, it would cool to what, 0? And it would still be cooler. Okay? So to me, the conditional instability, not only does it need to be between these two, but it also needs to have some moisture kick in at some point. That's what I think. Okay, very good. Whew. Okay, so this actually, it's hard to see the line, but again, the purple line is the weather balloon. Anytime the parcel of air has a temperature that is to the left of that purple line, it means that it's cooler and is stable, and anytime it has a tendency to fall. And every time it's over here, and so actually you can kind of see the crossover right about here. Okay, where it crosses over. But like I said, that blue line right there, that is when condensation has begun. So I believe if condensation did not begin, you wouldn't have seen this. All right. So stability and clouds. Unstable air basically wants to rise. And when we talk about clouds in chapter 5, when we talk about clouds, we're going to see that those are your fluffy sort of clouds. Okay, we call cumulus clouds. Okay, stable air tends to, if it does form clouds, is going to be our flat stratus type clouds. May or may not bring precipitation. And last but not least, and I think the video addressed this a little bit, if you do have kind of a, it's neat because Mother Nature thinks of her people, because like usually the earth is set up so we have kind of an ongoing kind of refreshing sort of, it's gentle, but we always think of wind as going like this. Actually, there's a gentle wind that's going like this all the time. It's called an updraft, okay? But if you are under a stable condition, basically that updraft is shut down. And temperature inversion creates a lid, so it kind of puts a lid on that going up. So let's just do a few slides in chapter 5. So I did not pull up this homework. I hope you guys will be okay with it. Okay. Chapter 5. All right. This bit about clouds. I just think clouds are beautiful. And the problem with clouds, or the reality of clouds, is sometimes you'll see more than one cloud at a time. Oh, you guys need these. I'm sure you would have told me. More than one cloud there. So what I'll do probably, since I didn't look at chapter 4, that's going to be due for most of you next week, is I will kind of look at it and push something out on Twitter, just if I have any suggestions about how to work them. So, all right, clouds. One of the things that I was hoping that you're already kind of picking up on is when you see a cloud, that's basically water that is in its liquid or its solid state. There's a certain amount of humidity in this room. Humidity is water vapor, and we can't see water vapor. But for instance, and I think I mentioned this before maybe, when you exhale on a cold day, okay, you see water, you see water, and it's not water vapor now, it's actually water liquid, probably, water solid particles, okay, but basically you're seeing the water that has condensed from its vapor form. Oh, sorry, one more thing I wanted to mention. Emphasize this idea of scattering. One of the things we talked about before is that when light or when energy hits a particle, it can do a few things. That particle can just transmit the energy, that particle can absorb the energy, or that particle can just redirect it. And that's actually what the liquid particles, the cloud droplets are doing. They're just scattering it, redirecting it multiple times. Okay. So we're going to talk next week more about the development of the cloud particles, but they always start with actually something called cloud condensation nuclei, or CCN. Now we've run into several little acronyms like ELR, DAR, WAR, okay? What other one? Oh, LCL, lifting condensation level, right? Now you got another one, CCN, cloud condensation nuclei. This is why your mother says do not eat snow. Okay, because actually precipitation usually needs something to kind of form around, and that's called the cloud condensation nuclei. We're going to talk in the end about cloud seeding. Maybe you've heard it before. Basically taking, where there are no clouds and taking an airplane and having it deposit something in the air and it's depositing cloud condensation nuclei to get the party started. So cloud condensation nuclei come in 2 flavors. One loves a party. Okay, that actually must be coming up on the screen. So cloud condensation nuclei, they get the party started, but they are not the only thing. So when we get talking next week, we're going to see that there's something else going on behind the scenes after you get the party started. So cloud condensation nuclei, they're most abundant like near the Earth, near the surface of the Earth, near the geosphere. Examples of cloud condensation nuclei would be dust and pollen, and actually sea salt makes great cloud condensation nuclei, and all of those things are abundant like here in the lower troposphere. When you get in the stratosphere, basically no cloud condensation nuclei to get the party started, let alone the air is very dry up there. So what I started to say is there's 2 types of cloud condensation nuclei. There's those that love it and those that do it very reluctantly. So the word phobic means fear of. So here where we say hydrophobic, those are the ones, and hydro means water, so hydrophobic cloud condensation nuclei sounds kind of like an oxymoron. You're like, dude, you're going to get the party started, but you don't like water? Well, yeah, okay. And those sort of cloud condensation nuclei, they probably only work if basically you have, we talked about RH, relative humidity. If you're at 100% relative humidity, you're at saturation, right? And we said you can go ahead and some sort of condensation can happen. Well, these guys don't like water, so basically you have to be above 100% relative humidity. We'll talk about how you get there. But the other ones, like a party, hygroscopic, actually then loves the party, and actually they can get it started below saturation. Okay, so let's take a look at the 10 cloud types, kind of like we saw on the video. We've been talking about stable atmosphere and an unstable atmosphere. So stable basically doesn't want to rise. And so then the clouds actually are kind of nice and flat. And actually they're going to have prefixes like strat, okay, stratus. The other one are fluffy, and they come from air that does want to rise. It's unstable. And they're going to have cum or something in their name. The other thing, and I like the figure that is coming up here in a minute, is we're going to talk about 3 elevations. We're going to talk about this elevation here. Okay, they're all in the stratosphere, by the way. They're all definitely in the stratosphere. This is low, okay, then we're going to have a middle, and then we're going to have a high. Now, if your cloud is low, okay, you don't have to say it's low. But if it's middle, you have to say alto. If it's high, you have to say cirro or something, okay? So if it's low, you don't say anything. Middle, you say alto. High, you say cirro, cirrus. The other thing, and the video we watched said this, we have 2 types of raining clouds, precipitating clouds, rain or snow, precipitating clouds. And nimbus means precipitation. So you're going to see NIM or nimbo or nimbus as part of the name of that cloud if it's precipitating. There's 2 of those. We have a flat precipitating cloud, and we have a fluffy precipitating cloud. This is our thunderstorms. Okay, this is our flat one. All right, so with that in mind, one last thing. So the thing is we actually, this is just the fluffy ones. Okay, we have 3 fluffy clouds. And you're like, I don't know where, this is only if you're looking at the cloud. If you're outside and you can actually see the cloud, this will work. If you're looking at a picture of the cloud, it's really hard to tell, which elevation it is. But basically, it looks like this. If you can go ahead and hold your hand out, and we do some things like this in astronomy too. If you extend your arm, okay, a few things. Basically, the ones that are lower will be bigger. So if you extend your arm like this says, the size of the cloud will be about the size of your fist. And that's kind of that is a cloud that's here in this level, and we call that just simply cumulus. Okay, cumulus cloud. Not a cumulonimbus, but a cumulus. Now, if you extend your arm and your thumb covers it, okay, that means it's up in the middle. So we're going to call that alto cumulus. Okay. If you extend your arm and it takes just your pinky to cover it, then that means that's a very high cloud, okay, and that would be cirrocumulus. Okay, so we kind of have the fist, the thumb, yeah, and the pinky. Okay, and by the way, do you kind of see these? See the CU, AC, and CC? I don't really have you guys memorize those, but each of the 10 cloud types has 2 letters that describes the cloud. So CU is cumulus, AC is altocumulus, CC is cirrocumulus. Oh, by the way, the other things, before I forget to mention it, send you home, is if you guys looked, like your textbook, the last, it's like a hand fold-out thingy. This right here. Since everybody loves clouds, it is your cloud guide. Your guide to the clouds. Did you guys know that, like, I guess Walt Disney, like, looked at clouds and came up with some of his cartoon characters? Oh, that's wonderful. Okay. So here we go. Here's the figure from your textbook. And you can kind of see the 3. You see the low, middle, and high, right? Okay. So starting with the high, we have kind of some variations. To me, unfortunately, the highs actually kind of have 2 flat clouds. The cirrus are the highest. They're highest and flat. And then cirrostratus are a little bit lower, but they're still pretty high up. To me, you can tell the difference between these 2 is the cirrus ones will be look even wispier. Sometimes they call these mare's tails. like as in horse. Mare's tails, doesn't kind of look like a mare's tail. Well, this one over here, this is like the pinky, right? Cirrocumulus. So it's, your pinky covers it up, and it's fluffy. It's not like a sheet, okay? The video we saw called the mackerel skies. Okay. The middle ones. Now, I said if you were high, you had to do cirro or Sirius or something. So hopefully you're kind of finding your way those three high clouds. Cirrus, cirrostratus, cirrocumulus. If it's middle, you use the word alto. So we only have two middle clouds. We have an alto flat and an alto fluffy. Alto stratus and alto cumulus. And again, this would be about the size of your thumb, the alto cumulus. Alto stratus, actually both of these, I like this figure a lot because the video we watched said that both cirrostratus and alto stratus, a lot of times they're thin enough that you can actually see the sun through them. When we have a slide that talks about how do you know you have an alto stratus cloud, sometimes they say it makes the sun kind of appear watery. You can actually see the outline of it. Okay. Let's see. Low clouds, we actually have 3. Okay. Now I call, well, let's see, let's just start from this one over here. Stratus. If somebody says I have one of the 10 cloud types and they say it's a stratus cloud, the fact they didn't call it alto stratus, the fact they didn't call it cirrostratus, means that it's here. In this next chapter, this chapter 5, we're going to talk about fog. And honestly, fog is basically a stratus cloud. Okay. So it's an example of a stratus cloud. All right. Well, say you have a low cloud, but it's got some fluff to it. I'm going to go over here. Say you have a low cloud, and it looks fluffy, a little bit of instability there, and it's about the size of your fist. Okay, I would call that a cumulus cloud. I would. Now, what your author does is basically say cumulus clouds can start here and they can actually tower up. So they have something, what we call cumulus clouds, have what we call a vertical development. But to me, cumulus clouds are here. My least favorite cloud, and actually the video talked about it, is this one, stratocumulus. You're like, really? I thought strato was flat, cumulus is fluffy. You're telling me there's a cloud that's flat and fluffy. Okay, and the video kind of tried to show you, talk you through that. Stratocumulus clouds, the fact that there's no alto or no cirro associated with it, stratocumulus has got to be relatively low. Okay, and again, they kind of have a layered look, but they have a little fluff to them. My least favorite type of cloud. Then the last two we have are the raining ones. So this is our first raining one, nimbostratus. Nimbo is the kind of showing you it's raining. Stratus is showing you that it's flat. So it's flat and raining. Okay. And then the last precipitating cloud has to have the word nimbo in it. Actually, it's gone with nimbus, and instead of a prefix, it's a suffix. So cumulonimbus. Cumulo meaning fluffy, nimbus meaning raining. Fluffy, raining. Those are your thunderstorm clouds. And I don't know if it's Unit 3, maybe. Maybe it's Unit 4, I think. We talk about severe weather, and we'll be talking about that vertical development. Okay, vertical development. So cumulonimbus clouds. Okay, well, I think that's a good place to stop. So I'll probably take a quick look at this on next week after I give you back your test. And then we'll kind of do some more descriptive stuff and do it that way.